So on our last lesson, we left off having figured out the Lie vector space, the Lie algebra, with the caveat that we really haven't made it into an algebra yet. We only understand it right now as a vector space. But we've discovered this vector space that's associated with this Lie group of 2 by 2 matrices. So from now on, we're really only talking about matrices, matrix groups or Lie groups that are understood in terms of matrices. That's the only thing that is of interest to me and really of this course. So Lie groups in the abstract, we're now thinking about matrices. So we've figured out these Lie groups of matrices, and we've discovered these vector spaces associated with their infinitesimal generators. And so now what we know this to mean is that if I draw this manifold that represents the coordinates of the actual Lie group of matrices, then I know that as long as I am infinitesimally close to the origin, right, I can find a generator that will take me from the origin to this infinitely close point and give me a very, very, very good approximation of what the matrix should be there. So if the relevant generator is given by lambda mu x mu, where notice I've converted a, b, and c into the numbers 1, 2, 3, so I can use this notation. This represents a generator that will produce this infinitely close element, because this number, although remember lambda could be very big. Lambda is there just to divide the proportions of these matrices up to give you a line. This whole thing is small because I slap in front of it a small number epsilon, right? So I'm going to put in a small epsilon. And I now know that this point, the matrix of that point, is going to be the identity matrix, which I'll just write as the number 1, plus that small epsilon times this thing here. So for example, if we took lambda 1 to equal some small number, which we'll call delta A, and lambda 2 equals lambda 3 equals 0, then the new matrix would be 1 plus, let's just say lambda 1 equals lambda 1. 1 plus epsilon lambda 1 x1, right? And so this matrix is going to be 1, 1 plus epsilon lambda 1. We can absorb, since epsilon is small, we can absorb them both together, right? So we can just say that this thing is just epsilon, right? And x1, right? Well, x1 will be, so it'll be epsilon 0, 0 minus epsilon, right? And this small amount is going to end up being 1 plus epsilon 0, 0, 1 minus epsilon, right? This would be the matrix that would represent the Lie group element, a very small distance epsilon, in the a parameter direction, right? Would be something like right there, I guess. Now, how much do we miss by? Well, what we're doing is BC is 0, so that's pretty good. So it's 1 over 1 plus alpha. So to the degree that 1 over 1 plus alpha is approximately equal to 1 it'd be 1 over 1 plus epsilon, is approximated by 1 minus epsilon. To the degree that this is accurate is the degree that this is accurate, right? It's linearized. So, but it's perfect. It's perfect up here, right? This is an exact replication because this is a linear expression to begin with. It's this one that hurts us, that makes us a little off. But again, as epsilon gets smaller and smaller and smaller, this approximation gets very much better and better. Okay, and we can do that for any different direction. So that is literally how the generators generate infinitesimal Lie group elements, meaning elements of the Lie group that are infinitesimally close to the identity, where these distances are all allowed to be infinitesimally small. All right, so now what about finite elements of the group? What about we want to get the exact group element in a finite distance away, where we can no longer assume that we're dealing with infinitesimal distances? So we've already done that once, but we're going to do it again in a little more detail with a more interesting group right now. All right, so the way we're going to do this is the way very similar to the way we described it in the previous version where we did this for in the abstract, right? We start at the origin, which is the identity Lie group element, where our target is some finite Lie group element. And we're going to take a bunch of very small steps so small that our infinitesimal prescription works correctly. And let me put one right there. And we're just going to do this an infinite number of times. So obviously we're going to be taking a limit. So how will that actually work in practice? Well, we know that we've got the identity, right? Plus we have a small number times an arbitrary Lie group element, which I've been writing like this, right? And this guy is our infinitesimal matrix. So what I want to do is I want to multiply the infinitesimal matrix by itself a lot of times, right? So if I was going to just do it a couple times, well, the way we want to write that now is we want to take this epsilon and make it a function of the number of times that we execute the multiplication. So I'm going to write that as 1 over n, and I'm going to raise it to the nth power, right? So as we take the limit, and that's what we're going to do here, I guess I should write that down, the limit as n goes to infinity, right? Everything takes care of itself because n gets very, very large, and this gets very, very small. So this becomes more and more accurate the larger n gets. The problem is you've got to take more and more multiplications to get this thing to work. But this ultimately here should end up being a finite group element. And which finite group element will it be? Well, it'll be the one in this direction, the lambda mu x mu direction, the one that's generated by this generator. So let's do that. Let's blow this thing up and see if we can actually make it work. So first part I'll blow up is this part right here. All right, so I blew up this and I inserted this here. So this is what this little term looks like, right? To go back to the notation before so I don't have to carry around these subscripts, I'm going to change lambdas into A, B, and C, right? The same parameters that we've always used. Parameter A, parameter B, parameter C. And that's because lambda 1, x1 was really A, x, A, right? That's the change I'm making here. That's just to keep it so I have fewer superscripts to write. So now what I'll do is I'll take this and I'll collapse that, right? Which is not very difficult because remember, this is a vector space. I just use matrix addition and scalar multiplication. So when I take A and I make it A minus A, when I take B and I make it 0B 0 0, and I take C and I take 0 0 C 0, that is your scalar multiplication of the vector space in operation. Then once I have that, I use the vector addition to add them together, and I get this matrix right here, A, B, C minus A, right? And then the n and the 1 over n and this guy comes all into play. And now I can take the next step, which, whoops, when I remind myself that I'm dealing with the limit as n goes to infinity, that this is really equal to the sum from n equals 1 to infinity of this sum, right? This summation. That is by definition, right? We know that the definition of this kind of limit is equal to this power series, right? We know that because this is the definition of the exponential function of the matrix A, B, C minus A. If the exponential function of a matrix seems weird to you, as long as this matrix satisfies certain boundedness conditions, which are pretty easy, these formulas work just fine for matrices like they do for real numbers. So this is the definition of the exponentiation. So we write it this way, and the power series, the Taylor series of that, is identical to this, and it's an entire function. So this exists everywhere as long as this matrix is bounded. And so now it's just a matter, can we evaluate this? Because remember, this is supposed to equal a finite member of the Lie group, and it's supposed to precisely equal a member of the Lie group that represents a finite displacement from the identity. So that we've got to get this right. This had better ultimately be equivalent to this, right? So we want to, and this is a matrix, right? Because remember, this is you can execute matrix multiplication, and you can execute matrix addition. So that's all good. But notice that the matrix multiplication concept, that doesn't exist inside the vector space yet, right? We haven't talked about multiplying matrices inside the vector space. So when we think of these group elements, these vector space elements, we have addition between them that we can talk about, and we can multiply them by real numbers, right? We can do all of that, but we don't really know anything about multiplying matrices. However, this step here to produce this guy, we're not producing a member of the vector space. We're producing a member of the Lie group, right? So one time we were, I guess I should draw this again. So what we did was we started from our parameterization of the Lie group, derived these elements of this vector space we're working with that involves these generators of infinitesimal transformations. And now we can add these guys together. We can add x1 and x2 and x3 and linear combinations of x1, x2, and x3. And all of those will be closed inside this vector space. But the operation we're talking about now, this infinite multiplication over and over again, that goes back here. Because remember, when we created I plus epsilon x, when we created this and we said that was an element of the Lie group that's close to the identity, that's when we get matrix multiplication working, right? Matrix multiplication exists here for Lie group elements. That's how two Lie group elements combine to form a third, right? The group operation is defined in such a way that every group element that becomes a matrix, if I take two group elements, get their matrices together, do regular matrix multiplication, I get a third matrix which is also in the group. So here, group multiplication is very clear, right? That's not the case here. These are matrices, but there's no matrix multiplication defined. So what I've done is, what is true is that if I take any element in this vector space, add it to the identity with a small epsilon in here, this guy sums to be a matrix that's also in this vector space. It just so happens that matrix is also an incredibly good approximation to a matrix that's actually in the Lie group. So therefore, I can take I plus epsilon x and I plus epsilon x, and I can multiply them as members of the Lie group to get another member of the Lie group. This guy here will not be a linear combination of x1, x2, and x3, however, because now I'm breaking out into a new form of operation defined in the group, not in the vector space. Now, ultimately, I keep saying this vector space will have a multiplication defined on it, but it's not going to be this. It's not going to be straight up matrix multiplication. It's going to be commutation, which is an altogether more complex idea, and we'll see why in our upcoming very soon lessons. But this is really important to understand. The generators form linear combinations. The generators are a basis of a vector space. Any linear combination of those generators is another generator, and each of those generators can be used to create an element of the Lie group that's infinitesimally close to the identity. And if you take two elements of the Lie group that are infinitesimally close to the identity, and you use, which are matrices now, because everything here is a matrix, you can do matrix multiplication to get another element of the Lie group. But that will not necessarily, or almost certainly not be an element of the underlying vector space. So when we go back to here and we look at this guy, these matrix multiplications are happening in the Lie group, not in the vector space, because there is no multiplication in the vector space. Okay, hopefully that's clear, but let's see if we can tease this apart and actually execute this multiplication. I have a feeling it's going to be kind of annoying. All right, so let's see if we can give this sort of a brute force try here. This is the formula we're working on. Let's just kind of break it down term by term. Usually the way this works, the brute force approach is you break this down term by term, and you look for, and then you raise it to each power, right? Oops, I don't have my power up here. There's got to be an n. So each term gives you a different power, and you kind of see a pattern that can express itself in, you see a pattern, so you don't have to calculate an infinite number of terms. You write down the pattern, and then you can infer the value of each of the matrix elements from the pattern. So let's see if that works here. So the first term is just the identity element. The second term is this to the first power, so that's easy. The third term, which is n equals 2, is 1 over 2 factorial times this matrix times itself, which I calculated as a squared plus bc in the diagonal elements, but then these two guys cancel as far as I can tell. Let me double check that. Yeah, they seem to cancel to me, so that's 0 and that's 0. So now we need to do some more terms. So when I do it for the n equals 3 term, I'm using the notation. Gilmore has this example, by the way, from another book, a different book than the one we're using. But it's a good example, so I'm running through it, but I'm trying to work it out. If you call this theta, right, that's the substitution, we'll call that theta and call that theta, then, so I guess I should write down theta equals a squared plus bc, right? So if I call that theta, then this result, the n equals 2 result, is this matrix. So the n equals 3 result is that times this, which ends up just being theta times the original matrix. Theta as a number times the original matrix. And so now, when I go to n equals 4, what's going to happen is n equals 4 is 1 over, wait a minute. 1 over 4 factorial. And then the result will be n equals 3, which is theta times a, b, c minus a times again a, b, c minus a. But we know this product from the n equals 2 expression, right? Which is just theta, theta. That's this thing here. So I know that this is going to equal 1 over 4 factorial times theta as a number times the matrix theta 0, 0, theta, like that, right? So that's n equals 4. And likewise for n equals 5, I'll get 1 over 5 factorial, right, times, well, what it should be is it should be times a, b, c minus a to the 5th, but that's going to be 1 over 5 factorial times 1 over a, b, c to the 4th, which is this, right? So it's going to be times theta, theta 0, 0, theta times, one more time, a, b, c minus a, right? But then we just drop back again into the same product that we had right here, which is just theta times the matrix again. So this ends up equaling 1 over 5 factorial. Oops. Well, actually, right here, yeah, so this is going to be, well, actually, I should write here, I should write, I should have written, let's see, what should I have written here? This should be then equal to 1 over 4 factorial theta squared times the identity matrix, right? So that would have made this line a little simpler. Let me erase that. If I had done that, then this would just have been 1 over 5 factorial theta squared times the identity times a, b, c minus a, right? Which is obviously I guess it's 1 over 5 factorial theta squared a, b, c minus a, like that. So now this brings us back to this n equals 3 term, right? It's similar to the n equals 3 term, except I'm missing a 1 over 3 factorial here, 1 over 3 factorial. So now we can kind of think about this in terms of a pattern. All right, so I've just listed out the first 9 of these things, and you can kind of see how the pattern goes. You start with the identity, then you get your the generator matrix, then you get the identity times theta, which, remember, theta was a squared plus bc, right? So that was equals theta. So then as you proceed, you just get the identity converts to the generator matrix, then theta takes an extra power, and you get the identity, then you get the generator matrix to the same power. So you always get 2 of the same powers of theta alternating between the identity and the generator matrix. And this pattern goes on forever. So the question is and I have the advantage, of course, knowing how the answer ends up, but the idea is, how do you calculate? What we're trying to do is we're trying to find an expression for each of the 4 matrix elements of a Lie group element, right? So we're going to add these things up infinitely, matrix element by matrix element, right? So the first matrix element would be 1 plus a plus 1/2 sigma plus 1 to the 3. Shouldn't be 1/2. Yeah, it is 1/2, but it's then 1 over 3 factorial, not sigma, theta a, 1 over 4 factorial theta squared, and we're gonna do that addition forever. But I kind of know how this works out, so I'm gonna split it up into the even component, the even powers of theta, and the odd powers of theta. All right, so this is what we have now. I just realized that this definition that I use for theta, actually the definition that Gilmore used in this example was theta squared equals this. Let's proceed without that and see what happens. But I'm going to take the n equals 0, n equals 2, n equals 4, and add those up in this upper left matrix element. And let's see what we get. And this is the answer. That is, this sequence, 1 over 2, 4, 6, oops, this should be 8, only the even numbers, will appear. These are the terms, right? This n equals 2 terms, 4, 6, and 8 term, n equals 0 term. And then I have theta, theta squared, theta to the third, theta to the fourth. So that's adding this to this to this, right? Well, I guess to this, whoops, this, that, and then that all together. Now this is where this squared comes into effect. If I had done the definition correctly, where this was theta squared, then this would have been theta squared, theta to the fourth, theta to the sixth, theta to the eighth, and that would have immediately sparked your recollection that this is the hyperbolic cosine of theta, cosh theta. All right, so now we'll transition to this definition for theta, which, going back here, as soon as I introduced it, where did I introduce it? We introduced it right here, right? This should be theta squared, 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 theta to the fourth, right? And this would be theta, that would be theta to the fourth, right? Okay, so I've readjusted that definition. Notice this does put a constraint. The a squared term will always be positive, but b times c is going to have to always be positive for this to work. Okay, so we've done this matrix element. What about this matrix element? Well, let's do the other diagonal matrix element. Well, actually, I shouldn't be so fast. Hold on. We've done the even terms of this matrix. The even terms of this matrix element, right? What about the odd terms? We have alpha, theta squared alpha. I better put those things here too. Okay, so now let's add for this for the 1-1 matrix element. Let's add the odd terms. So we get alpha, theta squared alpha, theta squared alpha, theta to the fourth alpha, theta to the sixth alpha, and theta to the eighth alpha. So the other terms we have to add are these guys, right? So these guys don't fit any obvious pattern, but I can definitely pull out the a, right? So the a can come out. So let's do that. So I just pulled out the a. I made a correction here. This should be theta to the sixth power. I had it written down as 7 there for some reason. Because it's very tempting to write it down at 7, right? I just did it again. Because if the factorial underneath is 7, you're expecting the 7th power of something in a legit Taylor series. But this doesn't quite meet, this isn't quite legit, right? That's the problem. The problem is that these powers are 1 less than these denominators. So this isn't some Taylor series that I recognize. And plus it has this 1 here as well. So it's got that 0 power. However, if I multiply this whole thing by theta, right? So say I did this. Say I multiplied it by theta over theta. Well, then this numerator theta would move inside, right? And so I would get alpha over theta, and then I would get a theta here, and now all the powers would suddenly line up, and then I would recognize this as equaling a over theta times the hyperbolic sine of theta. So that is all the terms. So then the answer is that this 1-1 element is the hyperbolic cosine of theta plus a over theta times the hyperbolic sine of theta. And that's, so we have solved for the 1-1 term of this, we've solved for the 1-1 term of that summation. Where's the summation? Oh, here. This summation here. We figured out when you take this infinite sum, you're going to end up with a matrix, and that matrix, that 1-1 term, is going to be the cosine of the square root of a squared plus bc plus a over the square root of a squared plus bc times the hyperbolic sine of the square root of a squared plus bc, right? Because theta equals the square root of a squared plus bc, and theta squared equals a squared plus bc, which that was the mistake I made in my substitution early on. So anyway, I've now solved for what this matrix, I've solved for its 1-1 element, right? And you can go through this exact same process and solve for the other elements. And what do you end up with? And if you proceed, you will end up with this whole thing right here. Okay, so this now is an element of SL2R. We have now parameterized it, again, using A, B, and C. It looks like we've got theta in there, but remember, theta is just A squared plus BC. And you'll notice that this resulting parameterization that we calculated is not the same parameterization we started with. It's not the same thing. And that's an important point. There's many different parameterizations of these Lie groups, and deciding whether two matrix groups are the same by looking at two different parameterizations, that's not totally trivial. And but that is important. And it's also important to understand that these Lie algebra, or these Lie vector spaces, as I'm going to call them for now, until we promote it to an algebra, I'm not going to call this what it is, which is the Lie algebra, but this vector space of infinitesimal generators of this Lie group could represent infinitesimal generators of different Lie groups, right? Different Lie groups can get you to the same set of infinitesimal generators, as I mentioned before, and we'll have to talk about that. So in review, what did we do today? What we did is we took a Lie group, a new one for SL2, right? SL2R. We took that matrix group. We discovered a parameterization for it, which I gave us, right? We started with we started with a given parameterization right here, right? We started with this parameterization, and from that parameterization, we calculated the infinitesimal generators. And then we took those infinitesimal generators, we took an arbitrary infinitesimal generator, which was represented as some arbitrary linear combination of the infinitesimal generators generated by each of the parameters independently. We took that arbitrary infinitesimal generator and we executed a limiting procedure multiplying the Lie group element associated with that infinitesimal generator with itself over and over again an infinite number of times. We understood that this guy in here is not an element of the vector space of infinitesimal generators because you've got this multiplication thing going on. And that multiplication thing will allow additional matrices to appear that are not members of the vector space. So this guy is not a member of the vector space. We interpret this guy here as a member of the Lie group, and the multiplication is executed in the Lie group, not in this vector space of infinitesimal generators. Then after we did that in principle, we executed that sum, right? I guess where was that sum? We executed this sum by recognizing that it was the definition of an exponential, and we determined that the sum looked like this. And then we said, all right, let's just brute force this thing. Let's calculate n and hope some clever thing appears where we can generate a pattern. And that's exactly what we did. We calculated each term, and we noticed a pattern. We created this parameter. I shouldn't call it a parameter because A, B, and C are the parameters of this Lie group. But we created this combined expression theta, which was a combination of the parameters. And once I defined it correctly, we were able to see a pattern develop. And then we just calculated each individual matrix element by summing these matrix elements together. And we ultimately ended with this parameterization of our Lie group SL2. Okay, so that's giving you a sense of where we're headed here. The next step is to start looking more closely at this and promoting this into the Lie algebra of this Lie group. And that'll be, we'll get started on that in our next lesson.